This presentation is part of our Advanced Simulation Techniques overview at the Stanford Linear Accelerator National Laboratory. We will focus on a crucial challenge facing the future of computing and high-power electronics: heat management. The title of our presentation is Two-Phase Cooling Simulation with Application to Microelectronics. Here is the outline for today's presentation. We will begin with the problem statement and our goals and objectives. From there, we'll briefly review the key theory behind computational fluid dynamics, CFD, with an emphasis on two-phase flow modeling to ensure everyone has the necessary background. Next, we'll walk through a step-by-step setup of the problem in ANSYS Fluent. This will help illustrate not only what we did, but also why each step matters for accuracy and convergence. After the setup, we will review the simulation results, focusing on flow patterns, pressure and velocity distributions, and phase interactions. We will highlight the critical insights gained from the model and compare them with expected physical behavior. Finally, we will discuss how to correctly interpret and apply CFD results in real engineering scenarios, including common pitfalls, validation considerations, and guidelines for using the data to inform design decisions. So with that overview in mind, let's get started. As the demand for faster, smaller, and more powerful microchips intensifies, so does the amount of heat they generate. Traditional cooling methods, such as air cooling and single-phase liquid cooling, are quickly reaching their limits. We're now dealing with heat fluxes that resemble nuclear reactor cores packed into tiny silicon chips. This is where two-phase cooling comes in, offering a transformative solution. Simulation-driven design and design parameter screening is an essential step in developing next-generation cooling technologies. In this project, we use ANSYS Fluent to model two-phase boiling using the semi-mechanistic boiling model. Our goal is to understand nucleate boiling and the pressure drop inside a microchannel cold plate. We also evaluate how close the system operates to critical heat flux, where vapor blankets form on the fins and can lead to rapid thermal failure. The boiling curve shows that as the wall temperature rises above the saturated liquid temperature, heat flux increases. As shown at ONB, bubbles begin to form, and latent heat transfer greatly boosts heat removal. However, this benefit disappears once a vapor blanket forms on the surface, which sharply reduces heat transfer and can lead to thermal runaway. We use RANS turbulence models in Fluent together with the SMB model to simulate conjugate heat transfer, capturing both fluid flow and heat transfer effects between the solid walls and the boiling fluid. The SMB model assumes a homogeneous mixture, neglects local bubble interactions, uses bulk properties for Reynolds number, requires a user-defined boiling model, and splits wall heat flux into nucleate boiling and single-phase convection components. Defining the water phase diagram in Fluent is essential for two-phase modeling with SMB. It provides the saturation temperatures and properties needed to capture phase change accurately. The real gas properties table ensures Fluent can predict nucleation, boiling, and vapor formation correctly, allowing reliable simulation of heat transfer and pressure drop in microchannels under two-phase conditions. We begin with a simple case that can be experimentally validated. Please refer to part 2 of this recording that covers Fluent implementation for this simple two-phase problem. We cover CAAD model preparation, meshing, Fluent model setup, and post-processing. After we review this simulation, we move on to a more detailed analysis focusing on microchannel design.